Hi everyone, welcome back to our walkthrough series. So next up we have this question number 3, which is about phasor analysis. Okay, so if you're not too familiar with phasors, or if you want a refreshment on what phasors are, properties, you can take a look at the walkthrough video for question number 2, where this is outlined. Okay, so in this question, we're actually going to apply phasors to solve a real-world uh, circuit problem. Remember when I said that we are using phasors to solve circuits in order to avoid having to solve differential equations? This is the time. So in this very question, we're considering an RC circuit uh, with a voltage source that is sinusoidal. So meaning that it can be written in the form of V0 cosine of omega t plus phi. Okay. So if you want to think about this question, as always, just click pause on the video and 3, 2, 1, and pause. We're going to go over this question together. So in this question, uh, we're trying to do phasor analysis, and there are 5 steps outlined in this question. So step 1, we want to convert VST into an exponential and write out its phasor representation, Vs tilde. So since we know that Vs of t can be written as V0 times cosine of omega t plus phi, we know the V0 is actually here. The V0 here is actually 8, and phi is actually negative pi over 4. That means the Vs tilde is actually equal to V0 over 2 times e to the j phi, which is 4 times e to the j negative pi over 4. Okay. And that is the phasor representation of our input. All right. So step 2 involves transforming the circuit into phasor domain. So in this circuit, there is a resistor and a capacitor. We know that the impedance of a resistor is actually just R, and the impedance of a capacitor is just 1 over j omega c. Okay, so the impedance, if you sort of forgot, is defined as the ratio between V tilde over I tilde. And if you're sort of confused as to why that is the case, maybe you can revisit a walkthrough for question number 2, where this is explained in great details. Okay, so our third step would involve casting KCL and or KVL equations in phasor domain. So in this question, or in general, we know that since phasors are linear, we know that KCL can be turned into phasor domain. So in general, we know that since KCL, in general, since phasors are linear and KCL states, recall that KCL states that all the current passing through a node sums up to 0, right? Since phasors are linear, if we take the phasor representation of both sides, we see that the phasor current passing through the same node also sums up to 0, since the phasor representation of 0 is 0. Okay. Same goes for KVL. So KVL states that within a loop, the voltage drop across all the components sums up to 0. If we take the phasor representation of both sides, we see that within this loop, the sum of the voltage drop across all the components sums up to 0. Since 0's phasor representation is 0. So we still have KCL and KVL, and we can just analyze the circuit as usual. So step 4, solve for unknown variables. So we want to solve for I tilde and VC tilde. So we should notice that we have we have ZR being equal to R, and impedance of the capacitor, ZC, is equal to 1 over J omega C. And since we're in phasor domain, for all these components involved, we have a constant impedance, meaning the ratio between the phasor voltage and the phasor current is always a constant. And we also have the phasor versions of KCL and KVL, which means we can just treat all these components as resistors. Although the resistance might be a little bit weird, there might be complex numbers, as in the case of the capacitor. But anyway, we can still treat them as resistors within the phasor circuit. But we should be very careful about things because whatever we get out of analyzing in phasor domain, it stays in phasor domain. To convert back into regular domain, we have to apply the formula. So we see that I tilde is actually equal to Vs tilde over Zr plus Zc. Okay? We see that this is the case. And this has to stay within phasor domain. To convert it back into the regular form, we use the fact that I is equal to I tilde e to j omega t plus the conjugate of I tilde times e to the negative j omega t. Okay. All right. So then we just plug in the variables. We see that omega is actually equal to 10 to the third radians per second. R is actually, I actually need some more space. I'm just going to write it here. So I tilde is equal to Vs tilde over R plus 1 over j omega c. So this is ZR, this is ZC. And Vs tilde, we know it's 4 times e to the j times negative pi over 4. Over R, which is 1 kiloohm plus 1 over j times, since the frequency again is 10 to the third, and the capacitance is 1 microfarad, so that's 10 to the negative 6. And so we see that this is equal to 10 to the third minus 10 to the third j. Whereas on top, we see that this is equal to 4e to the j times negative pi over 4. We turn the thing on the bottom to polar form to see that this is actually equal to 10 to the third times root 2 times e times to the j times negative pi over 4, which cancels out with the same term on the top, on the numerator. So we actually see that is actually equal to 2 root 2 over 10 cubic. I tend not to add a unit for that since it really doesn't make much sense in my personal opinion. All right, so we have the phasor current across the whole circuit. The computation is a little bit tedious, but typically when you're actually trying to solve for the I tilde, VC tilde, this is generally the workflow. You just analyze the circuit as if all the components are resistors. And then we just plug in I tilde to solve for VC tilde. Okay, I'm gonna write it right here on top. So we see that VC tilde is actually equal to ZC times I tilde, right? By definition, this is true. And ZC is equal to 1 over j omega c times 2 root 2 over 10 cubic. And so this is equal to negative 10 cubic j times 2 root 2 over 10 cubic, which is then equal to 2 root 2 times negative j. If we want to express things in polar form, will then just be 2 root 2 e to the negative j times pi over 2. Again, I wouldn't add a unit since, in my personal opinion, I don't think it makes a lot of sense to have a complex voltage. I mean, although we conceptually think of it as the phasor voltage. There's just a mathematical technique we're applying here. And as a final step, we transform the solutions we get out of the phasor domain back into the time domain, so the regular domain. So as we have explained, we just apply the formula. RT is equal to I tilde times e to j omega t plus I tilde's conjugate times e to negative j omega t. Okay. So we know that I tilde is just that. So we see that this is just 4 root 2 over 10 cubic times cosine of omega t. And okay, for simplicity, we can turn it into milliamps. So this is equal to 4 times root 2 cosine of omega t milliamps. Okay, and then for VC of t, we do the same thing. We just put in the phasor times e to j omega t plus the conjugate of the phase representation of VC times e to the negative j omega t. So since VC is actually this value, we see that is actually equal to 4 root 2 cosine of omega t plus minus pi over 2 volts. And that is our final results. What is the phase difference between I of t and VC of t? Just be this value. I mean, if your reference point is I of t, then the difference will be negative pi over 2. If your reference is actually VC of t, then the difference between the phase would then be positive pi over 2. Okay, so it's important to know that the phasor analysis only applies to sinusoidal inputs. Don't try to apply it to other kinds of inputs. It is a terrible mistake to make. All right, so that concludes it for our walkthrough for question number 3 on this worksheet.